Okay, so let's get started. I hope everything is working out with the projects and so forth. So now we're getting into the last couple of weeks here of the course. And today we will talk about local area networks and start to talk a little bit about specific standards and how things are done in a way in practice, practical protocols and so forth. So local area networks, Ethernet, and a little bit on how Ethernet networks could be bridged together using switches and so forth. But before we start, a short review. Last time we talked about ALOA and CSMA, various ways of accessing a common medium for several transmitters. So this is known as medium access. We talked about normalized throughput, which is the number of frames per frame duration that can be transmitted. So this S here, sometimes also denoted as rho, is the ratio of the effective rate, and this is the combined data rate of all transmitters which are using the medium, divided with the length of one frame in seconds and multiplied with divided by L. Let's see now, what is this now? L is the number of bits in a frame and X is the time it takes to transmit a frame. And then it becomes like the effective rate divided by the rate that the medium can carry, and this is also known as rho. And for ALOA, we saw a simplified analysis for this, is that S here follows this equation. This one for unslotted ALOA, or sometimes known as pure ALOA, and this for slotted ALOA. And these functions here are obviously depending on this variable g. And if one maximizes this over g to find the g which maximizes this and then calculate the maximum throughput, it becomes to be 1 over 2e for unslotted and 1 over e for slotted. And e is this natural number. Like e to the x, you know. G here is the average number of frame transmissions that are attempted per frame duration. And remember that frame duration again is this x seconds. So during x seconds, G frames are attempted, on the average G frames are attempted to be transmitted. And some of these frames are new frames to be transmitted, and some of them are retransmissions. So G is not the throughput, it's the attempts that we're trying to do, and S is the throughput. In equilibrium, S here is also equal to the number of new frames which are generated at the nodes which are attached to the medium. But that's only in steady state. Okay, so if one wants to improve on this, one can go to carrier sense multiple access. And it's a no-brainer type of improvement, because in ALOA, a station that has a frame that gets a frame from the upper layer just simply transmits that right away. So a more intelligent approach would be first to listen to the medium to see if something is ongoing, and if it is, then don't transmit, right? Wait somehow until the medium becomes idle again. So CSMA in a nutshell is that we listen to the channel or sense the channel as is known. If it's idle, that we don't hear anything, then we transmit. If it's busy, then we wait. Okay, so that's the general rule. Okay, the back-off strategies, the waiting strategies here, there are three main ones, or actually maybe just two. One is called persistent, and that's basically that if the medium is busy, then we continue to listen to the medium until it becomes idle, not busy, and then transmit then. So it's an aggressive transmission process. Non-persistent is basically if we listen to the medium and it's busy, then we draw a random timeout, random back-off time, and wait until that back-off time has passed, and then we sense the channel again, and we repeat that over and over again. So it's a more, what should we call, non-aggressive or polite way to do it. And then P-persistent is something in between. And here what we do, we sense the channel repeatedly until it becomes idle. If it's idle, then we transmit, but not with probability 1, but with probability P. Okay, so P is a parameter here. So if P is small, then if the channel is idle, then we transmit with the low probability. Okay, and if we don't transmit at this time, we wait a moment and then sense the channel again. If it's idle, then we transmit with probability P, and don't transmit with probability 1 minus P, and then we keep on doing this until we transmit. So this is a way of being a little bit less aggressive than P persistent. Persistent can be viewed as P persistent when P is equal to 1. That is, if the channel is idle, we transmit with probability 1, so we transmit. Okay, an improvement on CSMA is use collision detection, and this is possible for certain media, but not for all media. One media when this is not possible is for radio, or at least it's not really practical at this moment. There is some research in trying to make it practical, but for the moment it's not possible to do that. And we will talk about that more when we talk about Wi-Fi a little bit later. But anyways, if we can listen to the medium when transmitting, then we can detect if somebody else is transmitting at the same time. This is known as a collision, and if there is a collision, then we stop to transmit. So there is no need to transmit the whole long frame if we had determined already from the beginning that there is a collision, because we know that that frame would most likely be damaged and not received correctly. So there is no need to waste time on transmitting something that will never reach the destination. Okay, so we'll talk a little bit more about that today when we talk about Ethernet, because Ethernet is using CSMA with collision detection. Then we talked about, so these are known, the protocol CSMA and ALOA, they are known as random access. So here we have loose coordination between the stations, and then our quality of the service we can provide is not 100% at all times. So if we want to have something which is more controlled, but perhaps less efficient, then we can use reservation protocols, where we, before using the channel, we negotiate the access to the channel. And we negotiate that with all the other stations which are sharing the medium at this time. So a reservation protocol is organized in cycles, and the cycle consists of a reservation interval, typically consisting of mini-slots. And during the reservation interval, the stations negotiate who's going to access the channel at what time. And then it's followed by data frames and known in slots. And mini slots just indicates that the slots for reserving transmission is probably much less data here than in the data frames. So the data frames are much longer typically. Okay, and then the reservation interval then is used to coordinate transmission. Now, problem is that access to the reservation interval needs also medium access control, and here we could do two things. Either we use static channelization, so which means that each station which is attached to the medium gets a specific mini slot. It's the order in which one accesses the channel during the reservation interval is predefined. Okay, or one can use some type of random access, for instance, slotted ALOA or carrier sense multiple access or something like that in the reservation interval. And if we get the transmission in the reservation interval, we can reserve a transmission of the data a little bit later. Okay. So these are the two main ways to do it. We have also a method called polling. And polling is essentially that typically we have a master, and the master then asks the stations which are associated to the medium whether they have data or not to transmit, and then determines whether that station can transmit the data or not. One can do that with a master, or one can do that in some distributed fashion. And one typical example when doing this in distributed fashion is when we have something called a token ring, where the token is the opportunity, the right to transmit. So if I have a token here, for instance, this one happens to be a token, so now I can transmit, and when I'm done, I hand it over to the next person, and then that person can transmit, and then hand over the token to the other one, and so forth. So then it goes around, so it's very clear who's gonna transmit. In this type of topology, nobody is a master, everybody is equally worth, right? Of course, then there is problems when the token gets lost. Then one has to recover from this. Okay. Right. Channel resources, what are those? Channels, we talked about time slots when we talked about all these type of access methods. So that's one way of dividing up the channel. So we take the entire bandwidth, which is allocated to this system, and we split up the time into time slots, and then we hand out time slots to users. So that's called time division. We can also do frequency division, which means that we get different frequency bands in the system bandwidth. And these frequency bands we can access at any time. And then there is something, the third variation here, which is code division, where we are using specific waveforms that are different for each user. And if these waveforms have low cross correlation, they're almost orthogonal to each other, then it's possible for a receiver to distinguish the different users. Okay. So this is called code division. So this is used in 3G, for instance, and in Bluetooth and things like that. Frequency division, think of this as FM radio, for instance. And time division, good example of this, GSM, for instance, 2G cellular telephony use a type of time division. Question?
Is there any benefits from combining those?
Yeah, so typically system, so the question was, are there any advantages to combine this? And yes, there are. So typically, for instance, LTE and things like that, they're using combinations of time and frequency divisions. So now a channel is a time slot in a certain frequency band. Okay, that is advantageous when we have, for instance, a lot of bandwidth, but maybe not so much data per user to transmit. So if you get the whole system bandwidth, you can't use it, or you don't have use for it. So yeah, so their hybrids are quite common. Now, otherwise, it doesn't really matter how we cut up the cake, whether we cut it up in frequency or in time, we get as many pieces of the cake anyways, right? So it doesn't matter really. So what determines which channelization method to use, TDMA, FDMA, CDMA, or some type of hybrid of this, has to do with implementation issues. And that has to do with, how difficult is it to synchronize in time and frequency? How long guard intervals do we need in frequency or in time in order for the equipment to work as it's supposed to do? What is the propagation times and so forth? So these are more, should we say, depending on the medium and the type of access to the medium, one of these could be more advantageous than the other, right? So that's why you see different types of combination in different systems. Okay. So that was a little bit of a review. So let's move into the new part here. And we're going to talk about local area networks, or LANs. So what are those? Well, it's sort of by the name, local here means that it's confined to a small geographic area. So we think of that as a LAN, something which is not so large in geographical distribution. So physically small networks, distances, I don't know, up to kilometers or so. There is no fixed limit for this. It's typically used over a broadcast medium. So that we need some type of multiple access control for this. For the stations which are attached to the LAN, they need to negotiate how to use the LAN media. Hosts could very much move around. So for instance, Wi-Fi. So if I take my laptop here and I walk around and it's still connected, it will switch between different access points as we move around. So there is not a fixed location for the stations, typically. And then the addressing is done typically with physical addresses. So a network interface card, there are a couple of those in this laptop, for instance. Network interface card, or a NIC, is given a unique physical address. So the cards in this laptop has a address, and no other device in the world has the same address. So these are known as MAC addresses. So So a physical address or MAC address should be unique to the device. Now this is in theory because we can reprogram MAC addresses. So I'm pretty sure today there are 2 nodes somewhere which are using the same MAC address. I can almost guarantee that. But it's problem on the LAN for sure. We don't want to have a collision in addresses here. If that happens, then the whole thing falls apart and we need to recover somehow. So we're going to assume that this is true. Transmission over a wired medium is typically pretty good, right? The distances are small and so forth, so we have few transmission errors on the channel. What causes errors could be collisions of frames on the medium, but typically noise is not a problem. Transmission over this wired medium is close to error-free, I would say. So we don't need any sophisticated error control for this, very powerful error correction codes and things like that. For Wi-Fi, it's quite the opposite, I would say. Here, transmission errors are quite common, and here we need more sophisticated methods to deal with errors. We will talk today about these schemes that are on wired channels, where transmission is virtually error-free. LAN protocols, where are they? They are in the link layer. Okay, so where is the link layer? Well, if we remember the OSI stack, the lowest layer is the physical layer, and the layer above it is the data link layer. So we're quite close to the physical layer here. And the medium access control layer is typically just above the physical layer here in the OSI model. If we look at the IEEE 802 protocol stack, it looks something like this. So here, this is, as you know, if you remember, OSI is more theory, more ways of thinking, while Internet and IEEE, these are practical implementations, right? These are used. So sometimes these violate the rules that are here, but that's just how it is, right? So we're going to talk a little bit more about these today than the theories between protocol layers and so forth. Okay, so the IEEE 802 family of protocols is quite commonly used. I think most of us use them today, daily. IEEE 802, they define 2 or actually maybe 3 layers. Some physical layers, a bunch of them, and then there are some medium access control layers, and there are less of them, but still quite many. And then on top of that, there is a unifying layer called the logical link control layer. 802, why 802? Why not 702 or 33? There are conflicting views on this, but somebody says that it's just the number that was available at that time when this was started. I like the more colorful explanation of this, which is probably not true, but it's more colorful, is that this project was started in 1980 in February, so 82 for February. So all of these things are since the early 80s. Right? And for me, that is not so long time ago. For others, maybe this was a long time ago. But it's fairly new technology, right? Okay, LLC on top, and then we have these MAC layers, and then we have the various physical layers. So the MAC layers here, they provide unreliable datagram service. So basically, they transmit packets, but they don't guarantee anything. Okay, so all of these transmit packets and guarantee nothing, really. So the link layer here, the logical link layer control, can enhance this MAC service, this unreliable datagram service, and can provide either nothing, basically the same as what the MAC layer does, or reliable connection-oriented service. This is optional. Or acknowledged connectionless service. This is also optional. To my knowledge, this is by far the most common way to do it. And then if you want connection-oriented things, that is solved on the layers above it. Okay, but you could do that on the link layer if you like. At least there are standards for doing this. So on top of this, many protocols can exist, also concurrently. So we have, for instance, it could be IP or some other versions of it, of network layers on top of this. Okay, any questions so far? No? Okay. So let's look a little bit on this LLC and how that relates to the Mac here. So the LLC is on top of the Mac. By the way, I should say also that, no, I should not say it now. Okay, I'll say it later. So LLC and Mac PDUs. Okay, so this is the protocol data unit at LLC layer, and this is the protocol data unit on the Mac layer. Okay, so this is on top of that one. So if we look at the LLC PDU, it's quite simple in the sense that it has just a destination address and a source address. And then there's some control bytes here, 1 or 2 of them. And then there is service data unit. Okay, so from the LLC point of view, it gets a service data unit from the layer above. Could be an IP packet or something like that, right? And that is the blue part of this. And then it puts on these headers here. And the SAP addresses here, service access point addresses, they identify the protocols which are on top of LLC. Okay, so if LLC gets a packet, an IP packet, then this, the source address is 06. Typically goes to an IP entity at the other end, and then will be 06 here also. Okay. Or there is a bunch of other protocols here. At the moment, so if we have 1 byte here, how many protocols can we support above? One byte, 8 bits, how many combinations? 256, yes, exactly. 8 bits, 256 protocols. And this was thought to be quite sufficient at the time when this was specified. Turned out not to be sufficient. So in order to be able to address even more of these, one can have a layer which is called Snap. And either one can think of that as a layer above the LLC or an extension to LLC. And this makes it possible to address many more protocols than the 256 which were defined here. Okay, and it's quite used in practice actually. Okay, so this PDU is the service data unit for the Mac layer. Okay, so this what's in here puts in the middle here in the Mac layer, and the Mac PDU typically consists of a Mac header and a frame checksum. Exactly how this is done is depend on which Mac layer we are using, right? But if we are using Ethernet, for instance, this would indeed be the case. Okay, so we're going to talk about Ethernet, and Ethernet is the dominating LAN standard. And a little bit of history is that in 1970, Aloha was invented, or put in the field at least. So this was done in the Hawaiian Islands. And there was a guy called Metcalf who visited the people in Hawaii, and he and another person invented something they called Ethernet in 1973. In 79 it became a standard called DICS. In 85 it became an IEEE standard, and then there's many other evolutions of Ethernet following this. This is an original sketch by Metcalf in 73 or something like that. And his idea was that can one do something that's similar to Aloha but inside a cable? Okay. So instead of using radio transmission, he wanted to do this in a cable. So then he took a coaxial cable that he called the ether, or this is the medium that we are using. So one can look at this as some type of waveguide that electromagnetic waves goes back and forth. If we have a terminator here, it means that an electromagnetic wave doesn't bounce at the end here, which is nice. Otherwise, it would just keep on going for time eternity. And then if we have a computer, it can have some electronics here. And then one drill a small hole in the coaxial cable and inputs a transmitter part here, transmitter receiver part here. So here one basically takes the cable and drill a small hole in and put in a certain device into that, and that's the connection to the Ethernet. Okay, and ether, you know, that's the once upon a time, one thought that the electromagnetic waves needed some type of medium to propagate into. And then one realized, and we called that the ether. And then it turned out that it goes very well through vacuum. Actually, it goes extra good in vacuum compared to any other medium. Right? So the ether is not, historical reasons for this. Okay, and actually in the beginning, one said, okay, let's use a yellow coaxial cable. So this is not mandatory, but many of them were yellow in the beginning. Maybe one should find them easily, I don't know. Okay, so medium access controlling this. How is this going to be done? Okay, so now we're going to go back to what we learned about medium access. So how should we do it like this? Well, I mean, Metcalfe, he was inspired by ALOA, okay, which uses slotted or unslotted ALOA. And as opposed to the radio network here one can actually listen to the medium at the same time as we are transmitting. So if two stations are transmitting at the same time, this would generate a collision, and this could actually be detected by the station that's transmitting, and therefore we can abort the transmission. So here it makes total sense to use carrier sense multiple access with collision detection. So again, what do? We sense the channel. If idle, we transmit. If busy, we sense until it's free, and then we transmit. So here we're using persistent CSMA, okay, or one persistent CSMA. Now, if a collision is detected, what to do then? Then we should try again at some other time. And the way it's done like this is that if a collision is detected during transmission, then we stop to transmit the frame, but we transmit a short jamming signal. And the reason for sending this short jamming signal is to inform all the stations which are attached to the cable that a collision has occurred. Okay, and then we back off a random number R of mini-slot times, and then we start all over again, okay, by sensing the channel and so forth. Okay, so R here, what's R? We will see that in the next slide, but mini-slot time, this is a crucial system parameter, and we select that to be slightly more than twice the propagation time of the medium. Okay, we'll see in a second why this is the case. So the mini-slot time is roughly the duration of the contention period for this CSMA CD. And therefore, it's also equal to the minimum frame duration. We'll see in a second why this is the case. So in the beginning, if one thinks of having in the early days, 10 megabits per second was considered quite a fast LAN. So if we have 10 megabits per second, and the cable has a length of 2.5 kilometers maximum, and actually consists of 500 meters long cables, and then in between there are amplifiers, because otherwise the signal will be attenuated too much. So if we say we have 4 of these repeaters connecting 5 segments, then we get an effective cable of 2.5 kilometers. Then one can calculate a little bit, and then one gets twice the propagation time to be roughly 50 microseconds. And then the minimum frame length is then chosen to be 64 bytes, because it takes 64 bytes at 10 megabits per second is a little bit more than 50 microseconds. Okay, so that's how it was calculated. Okay, and why do we need this? Well, if you remember, if we want to do collision detection, where we have 2 stations which are attached to the medium, and suppose they are at the maximum distance from each other. So this is some distance. This was 2.5 kilometers in the example here. Then it takes some time for a frame to go from this end to this end, and this is then the propagation time. So both of these stations can listen to the medium and think it's idle and initiate transmissions that will collide. Okay, so this is possible. So in this simple example here, we have 3 nodes, and A starts to transmit at this point in time, and it takes some time before this signal is reaching node C, which is on the other side of the medium. It takes roughly 1 propagation time to do this, or it takes a propagation time to do this. So at this point is the latest point in which C can sense the channel, think it's free, and then initiate a transmission. So suppose it does that and it transmits this frame here. Then at this point in time, node A can detect that the collision has occurred. Okay? So it takes roughly 2 propagation times before, or rather, it takes roughly 2 propagation times after a transmission has been initiated until we know if there's going to be a collision or not. If a collision has not been detected at this point in time, we know that our frame has reached all other nodes, and all other nodes needs to back off. Okay. So if we have captured the channel, or we don't hear a collision for 2 t-prop seconds, then we have captured the channel and it's all ours. Okay, and then we can use it forever, or until we're done, rather. If there is a collision, then we detect that. Detection is not instantaneous, right? We need a little bit of time to detect the energy and so forth. So it takes a little bit of time here before everything is detected and so forth. And then we transmit a small, but we abort our transmission at this point in time. So this is known as the contention period. A contention meaning that stations during this time is contending for the channel, competing for the channel. And after the contention, either one has detected a collision and then one has to restart the process of contending for the channel, or one node has captured the channel and then can use it. Okay, so for collision to be detected during the contention period here, the frame duration here needs to be more than twice the propagation time. Right? Because otherwise we have completed our frame transmission before the collision occurs. Right? So if this frame, for instance, was destined to be, it can be damaged here. Collisions can, if the frame is not longer than 2 t-prop, then collisions can occur on the channel, which is not detected by the transmitter. Do you see that? Okay. So that's actually quite important. So there is a minimum frame time for this to work. And that on this type of LAN, we need the frames to be at least 50 microseconds long, which at this data rate corresponds to 64 bytes. Okay. All right. So that was about the minimum frame time and this slot time. Now, what to do here then if we detect a collision? Then we abort the transmission and then send the jamming signal. And then we back off R, a random number R, mini-slots times. Okay. So how to find R is now the question. Well, here we use in Ethernet, we use something called the binary exponential backoff algorithm. Sounds exciting. So how does it work? The idea here is that we would like to back off. Okay, so how should we select the back off time? Well, we want to make it as short as possible in order not to waste time. But we want it to be long enough so that stations who are contending for the channel are not trying to access the channel at the same time again. because that would generate a new collision, new back-off, new collision, back-off, and so forth. So here, there is always a trade-off. How long should the back-off be? And as we think about it, the back-off needs to be proportional to how much traffic is now currently demand for the stations which are attached to the medium. So if we think of all these stations here attached to the medium, if they don't really have much data to transmit, say that only 2 of them have data to transmit, so these 2 maybe, and then they collide. Okay. How long should they wait? Well, they need to wait enough so that these are not accessing the channel at the same time. Okay, so then the back-off period doesn't need to be very long in order for this to happen. The other extreme is when all nodes have data to transmit. So everybody's eager to get their frame on the medium. That would generate a lot of collisions, and then we need to spread out the retransmission times quite a long time in time. So we need long back-offs here in order to resolve it, because at some point we want one of these stations to be able to capture the channel. Okay, so the idea here is that the back-off time is r times t slot, where r is a uniform random variable between 0 and 2 to the power of k minus 1. So k here is depending on how many retransmission attempts we have done. Okay. This is known also as the selection window for r. It goes from 0 up to this number, 2 to the k minus 1. So if we at retransmission attempt n, then we select k to be the minimum of n and 10. Okay. So okay, so at the beginning, we have a frame that's ready to be transmitted. Okay, so then the retransmission, the number of retransmissions we have done is 0. Okay, and according to this rule, where k is the minimum of n and 10, then k is equal to 0 as well. If n is equal to 1, then k is equal to 1. When n is equal to 2, then k is equal to 2, and then we continue here rather boringly up to 10, where k is then k is equal to 10. After n is equal to 10, then k will stay at 10. So for 11, it will still be 10. For 12, it will still be 10. And then keep on doing this until we reach 16, and it will still be 10. Okay, so that's that the k is the minimum or n of 10 means that k will never be larger than 10. It will be equal to n for n equals 0, 1 up to 10. Okay, so if we have n here, and then 2 to the power of k minus 1, so this is the range, this is the maximum value that r can take on. Okay, for n equals 0, the maximum value that r can take on is is also 0. So this is r max. When n is equal to 1, k is equal to 1, and 2 to the k minus 1 is 3. Okay, so here, after the first retransmission attempt, r could be 0, 1, 2, or 3. Okay, so we wait 0 slots, 1 slot, 2 slots, or 3 slots. These are our, with equal probability, we pick that as the back-off time. If that doesn't work, so we still have a collision, then our second attempt, we will have 2 to power 2, which is 4 minus 1, so this is I don't know if I can calculate this correctly. It's like 2 to the 1 is 2 minus 1 is 1, right? 2, this is 3, okay. Now 3 then. 2 to the 3 is 8 minus 1, that's 7. Okay, so 1, 3, 7, 4 then. 2 to the 4 is 16 minus 1 is 15. So we see here that we are rapidly increasing the size of the contention window. As a matter of fact, it's exponentially increasing. In the retransmission attempt, at what attempt we are. Okay, so in the beginning we're quite aggressive. So we get a collision and then we assume there's probably not so many nodes which are contending for this. And then if we get 2 collisions in a row, well, maybe there are more. So we back off a little bit more, potentially back off a little bit more. We spread our backoffs more, and then continue to do that. And at the end, when we get to 10, we have 1023 as the maximum R max, and then it will continue like this until we have hit 16, like this. After 16 attempts, we give up. Okay, then something is severely wrong. Okay, it could be like the cable is broken or something. And then we just abort, we just throw away the frame, and then the higher layers have to deal with this. Questions? No? Okay. So that's how the binary exponential back-off algorithm works. So depending on the perceived load on the medium, we back off either not so much or quite a lot. Okay. So it adapts to the situation. So at high load, if one would look at the channel, how that would look at high load, then it goes through this typical cycle that suppose that there is a node, a station which has captured the channel, then it transmits its frame during this time, and here obviously the medium is busy, right? Okay, now during the time it's busy, then every station who gets a frame to be transmitting during this time will continue to sense the channel until we hit this time. And what's going to happen at this point? So suppose station, this is from that, these are the times when suppose station number 1 is transmitting this frame, and now station number 2 gets a frame to transmit here, station number 3 will get a frame to transmit here. What's going to happen at this point in time? Station 2 and station 3 will see that the channel is idle, and then they'll transmit. Exactly. So it will be a short break before they realize, the channel is idle, let's transmit. Okay, so they start to transmit their frames, and then after a contention period, they will realize, oh no, it's a collision, and abort. They will draw a random backoff, depending on which retransmission attempt this was, and then try a little bit later. Then maybe they draw the same backoff time, and there is another collision like this, and another collision like this. There is a number of these until somebody gets lucky and captures the channel. Okay, so it goes from busy to contention, and here's where nodes are competing for the channel, but nobody really succeeds. There's a lot of collisions here. These collisions have shorter duration than the frame duration. These are typically this 2 T-slot, roughly T-slot time. These. And then there is a new frame, from some station that got lucky. So here we are busy again. And what's going to happen here? Well, this is a new contention interval. So a number of collisions, and maybe there were only 2 collisions, and then there is the next frame. So this is typically what happens on Ethernet medium, or any medium which is using collision detection. Okay. Successful transmission, contention, 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 collision, collision, collision. Successful transmission, contention, contention, contention. Successful transmission, and we keep on going like that. Now, obviously, during low loads, when there's not a lot of data, the whole medium could be silent for extended period of time, right? But at high load, it will look something like this. Questions? No? Okay, so let's take a break then.